Okay, so I'm Hakan Millroth. I work for a company called Bluetail, which you may have met yesterday, appearing here. I'll talk about large-scale mail architectures. So now we're up at layer 7, but it still will be some routing. By large scale, I mean mail server installations with from a couple of 100,000 users and upwards. So there are basically three feature or distinguished features for any kind of ASP application, not just mail, that sets them apart from enterprise systems. One is the kind of scalability required. Another is high availability, since these are 24/7 systems per definition. And the last one is the ability to do management on the system while it's in operation. For the same reason, it's a 24/7 system. And to the right in this picture, you can see I try to illustrate that, okay, people know the best practices in the industry is quite advanced on how to build scalable systems, scalable web systems, scalable mail systems. Also, I have a fair understanding of how to build high availability systems. Not cheaply, but anyway, build them. But there is a extremely low maturity in how to build actually systems that can be managed while the service is up and running without disturbing traffic. So I'll talk about all three of these. Well, I'll talk mostly about, well, a lot about scalability, since that's the most understood of these problems. So the challenge here is really to build a scalable, high availability system which is not too expensive, that is easy to manage while the system is up and running without disturbing traffic. Okay, there are basically three base architectures for a mail system. One is the simplest possible one, where you have one mail server, either a single processor or a multi-pro, with a huge mail storage. Because this system for the first, it doesn't scale. Well, you can put in a bigger multiprocessor, but sooner or later you hit the roof for scalability. Another serious problem here is, of course, crash recovery. You either need a journaling file system or something like that to be able to quickly recover from a crash in a system like this. So this is quite uninteresting when we talk about large-scale systems. Next step up is shared storage architecture. By that I mean that you have several mail servers, you spread the load or the traffic among them, for example, by a level 4 switch or even DNS round robin. But all in this case, 3 servers share the same mail storage. So my mailbox can be accessed from any server here, which is the reason you can use simple load balancing gear in front of it. Trouble with this kind of architecture is the mail storage. It's, well, most you see down here a couple of alternative NFS, SQL database, some fiber channel system, and the common theme of this is that either they don't work very well, or they are very expensive, or they have both of these problems. Okay, so what I will focus on is what you see at most big ISPs when you look at their mail systems, a distributed storage architecture where the mail store is partitioned among a large number of mail servers. So my mailbox resides on a particular server and can't be accessed at all from another server. And in this case, the storage can be, well, cheap. It could be local disk. Typically, it's a DBM database, something like that, Berkeley database. But there are a bunch of interesting problems in an architecture like this. So the rest of the slides, the rest of the discussion will focus on this. Okay, so let's start with scalability. This is the first slide again. Scalability for an architecture like that is, we can divide that into 3 problem areas basically. Load balancing, and you'll see what I mean with load balancing in this case. Queuing, mail queuing, and message routing for SMTP, and session routing for either POP or IMAP, depending on how you read your mail. So, start with load balancing. When we have an architecture like this, a balanced load means that you have an even distribution of mailboxes on each server. Because the number of mailboxes on a server determines the load on the server. So load balancing is basically a manual operation of moving mailboxes between servers. Manual, preferably automatic in some way. And you sure need to do that for a number of reasons. One is that if you're a typical ISP, you grow quite fast, so you need to add more servers. And then you have to do a redistribution of your mail accounts from one server to another. And also you might have customers that themselves are growing, so you have virtual domains that grow quite fast. Okay, so this is what load balancing amounts to in an architecture like this. And a naive way of moving mailboxes would be to just copy them from a server to another, which is of course not working, because if this mailbox is accessed while you do it, you risk losing mail. So there's a simple algorithm for doing that. Okay, so the task here is to move a mailbox from server A to server B. What you do is that you first create the new mailbox and lock it, and then change basically the routing tables for mail transfer and session routing to the new mailbox, and that one is locked, which means that the POP user cannot access his mail at this point, and the SMTP inbound mail is queued. Okay, then you move the contents of the old mailbox to the new, and then you unlock the new mailbox, and then you're up and running. So you have a short outage here for POP users, which is hard to avoid in an architecture like this. Okay, next problem which has to do with the scalability is probably the most serious problem for a large mail installation, which is queuing. And the problem is basically that suddenly you got large volumes of queued mail or mail to queue for some particular domain. Typically some big and slow domain. There are a number of them, as you might know. Could be a number of causes for that to happen. One is that their mail servers are down. It's impossible to connect to them. Another is that you can connect to them, but they just disconnect, which means that you have to queue it and try to resend it yourself later. Or they can be misconfigured, either because they run some strange mail server software from some particular vendor, or that they have, what they do basically is that they send temporary error codes when they mean to send permanent error codes. And temporary error codes means that you have to queue it in your system. And when that happens, you can actually get flooded by stuff you have to queue, which can happen really, really quick. So this is a very common situation at I would guess, any big ISP. And it has to be handled. And the way to handle that really is to first to detect the situation very quickly. So you need to have an alarm system that actually monitors the queues, not only the size of the queues, but also the contents, so they can say that, whoops, now we have grown very quickly, and the reason we are growing is that food.com has 70% of the mails in the queue. So what we should do in that situation is somehow to create a new queue for that problematic domain, either on, if our software allows it, on the same host, or dedicate a relay machine for that particular domain. So that's how it should be handled. Very often, at least what I have seen, it's not the way it's handled because, well, it's really not supported in quite a lot of common solutions. Okay. Next thing that's important for scalability is message routing and session routing. And here the main issue is actually how to handle virtual domains, which you have quite a lot of if you're on a big ISP. You can do that in a number of ways. One way is to, for example, allocate a separate IP address for each virtual domain you host, which is probably not a good way to do it because it's not very scalable and it's hard to maintain. Sort of the SendMail way of doing it is to have a virtual user, for example, you see here my real mail address, and the ISP rewrites it. Either actually rewrite the SMTP command to my real name, or keep that knowledge internally in its routing system to some internal address that points to the server mail3 in this example, where my mailbox resides. If we have a rewriting scheme like this, we can actually move the whole Bluetail virtual domain by a simple regex matching between machines. Of course, other addressing schemes we can use. So examples of systems that support is SendMail. You use the alias file and the virtual user table for doing stuff like that. And there's also a draft for message routing based on LDAP directories. But if you do that for inbound SMTP, you better do it for POP and IMAP as well. Otherwise, the alternative is that you handle the inbound SMTP quite well, but your POP users are bound to connect directly to the mail server where the POP server where their mailbox is residing, which is not at all a good solution for a number of reasons. The most important one is that it's very hard to relocate that mailbox because it would require changing client software, which is a bad thing for an ISP. Okay, so typically I end up with an architecture like this, that you have a two-layer architecture. The bottom layer here is the actual mail servers, that's the endpoint mail servers, and the first layer, the two machines up here, that's a relay hub basically, where you do routing and also hook in all kinds of spam filtering you want to do, virus checking, stuff like that. And that's the address you publish in DNS. So the MX records for all virtual domains point to the routing hosts here. One good thing with that is that the IP addresses of the bottom layer mail servers here are not visible, need not be visible on the internet. So you can actually run this on a private network behind the routing hosts. Okay, so this is very common. I mean, most big ISPs have something similar to that. Okay, then you also have to handle both outbound SMTP and POP IMAP in a similar way. So you see here, what you should do in that case is basically to to extend the responsibility of this routing layer, the first topmost layer, to also directly handle outbound SMTP and POP routing and IMAP routing, which this picture illustrates. That the POP client goes it goes with one level of indirection as well, exactly as the inbound SMTP. Outbound SMTP, you connect your SMTP client to the message routers, and they decide what to do. And then, of course, they have to know that your client is to be considered to belong to the local domains, so you can relay from that client. So here you end up with an architecture basically where you do all message routing, all POP IMAP routing, all spam filtering in the first layer, and the second layer is basically reduced to POP servers, IMAP servers, and local delivery. So you don't even need to run a full-blown MTA like some make in the second tier here. So this is sort of the state-of-the-art scalable mail architecture. There is, though, one big disadvantage with this architecture, and that is that each tier 2 server here is a single point of failure, which means that you cannot wipe out the entire service, but if one of these boxes go down, say if you have 10 boxes, 10% of your clients cannot access their POP account until this machine comes up. And inbound SMTP is less of a problem since it gets queued. Outbound SMTP is not a problem since it goes in the tier 1 layer. But okay, you have an outage for some fraction of your users when it comes to POP access. So to handle that situation, you basically have to have a situation like this, where you have a hybrid storage solution that you have pairs in the bottom tier here. You have pairs of mail servers sharing the common storage, which is easier to handle by multi-home disks or some low-tech solution. You don't need a full-blown fiber channel storage area network to handle 2 machines. But it's also a matter of cost. I mean, it's not really serious that 10 or 2% of your users can lose access to their POP account at an outage, maybe. But if that's serious, this is what you end up with doing. Okay, so this is basically a quick overview of state-of-the-art in scalability and what you can do to improve high availability to the point where you don't get any outages at all visible to the outside. And the last issue here is the toughest one, which is in-service management. So what you really would expect in a 24/7 system is basically what people have been used to for public telephone exchanges for the last 20 years. That you can reconfigure it in a running system without disturbing traffic, that you can upgrade the software in it without disturbing traffic in a distributed system, and that you can redirect traffic to other points while you need to replace some parts of the system. And I mean, here we are extremely far from this in most installations that I've seen, and also in most commercial products, unless they're very high-end products. So I think this is the challenge to actually build a really, if you want to build a big, really big mail server farm, the challenge is actually to combine the scalability solutions, which are quite well understood, with a good storage solution and finding some way to solve this problem of managing it all in a rational way. Well, I have 10 minutes, so I have some times for questions.
We have some questions for Hakan. And maybe we have the lights. Thanks. Going once. Thank you, Hakan.